Welcome to the second set of exercises for our little audio signal processing SuperCollider course. These exercises relate to the first audio signal processing video and serve to verify some of the things, some of the theory from that lecture. So you have 5 exercises. What you can do is pause the video and try to do them on your own if you have some SuperCollider background. Otherwise, bear with me. Cool. So first up, we're going to verify the effect of lower frequency resolution and lower bit resolution by looking at the frequency spectrum scope, of a sine wave. Okay, so a good way of getting into building complex things is to do step by step and verify every step along the way. 1 kilohertz standard. So let's see if our scoping works. That seems to work. Okay, so how do we decrease the resolution? I mean, first of all, one of the things to note here is that that the sine wave doesn't look like an actual straight vertical line, and that has to do with the analysis, whereas theoretically it would be a straight line. But never mind that. Let's decrease the resolution and see what happens. So in terms of decreasing the frequency resolution of the signal, we're essentially trying to create a stepwise signal. And for that we use a technique which is called sample and hold, and in SuperCollider it's latch.ar. So we have the input signal as the first parameter to the latch, which is my sine wave, and then the second one will be the trigger signal. So this needs to be a signal that specifies when to take samples from the input signal, and a trigger in SuperCollider is a signal, or actually a moment, when the signal crosses from negative to non-negative, I believe, crosses the zero from below. So you can actually use anything you come up with. I can actually use another sine wave. Probably an expensive thing to do, but never mind that. So now we pick the new sampling frequency. So yeah, we're running originally, I believe, at 44,000. Although normally my stuff runs on 96k. Did it print out here? Sample rate 96k. Okay, so well, whatever. Let's try to run it at 10,000 hertz. Okay, so what we can do is first of all plot this to verify that. See, it didn't work. So let's see what's going wrong here. Does the plot of the S work? It doesn't work. Oh, pity. Does the play work? In has bad output. Okay, I did mess something up, which is, oh yeah, sorry, I've put the server in here, so that wouldn't work. See, good idea, test things as you go. Here we go, that's a sine wave, and then the one which has a compromised horizontal resolution, you could say. A lower sample rate looks a bit like this, so it's a kind of a stepwise thing. Okay, so that looks good now, and then we want to see what happens to the frequencies. So you hear it, and that's all the junk that we've just made. Okay, so the conclusion is we get junk. Can we predict what the junk is? Well, it is a quantization distortion. There is some aliasing in there as well. I probably wouldn't bet on predicting all those components if I think about it. I mean, one thing which is cool, possibly interesting, is we can listen to those components only. If I call this my latched signal, and then what I can look at is subtracting the original signal from the latched signal. So hopefully you're not totally annoyed by this sound. Oh, looks like that didn't quite work. I would have expected it to work if I subtract that sign from that. We're supposed to get the error signal, but it seems I'm still getting the sine wave. Let's see what happens if I plot that. Well, that indeed looks like an error signal. But yeah, I mean, silly me. The thing is that this signal is again periodic at that same frequency. So I do get an error signal, and well, could be cool. I mean, looks nice. Anyway, that is then the reduction of sample rate, and then we can do a reduction of bit rate, which means that we compromise the vertical resolution. And we do that by rounding our signal, and then I can specify what we are rounding it to. That should do something. Let's see if that does something. I can't quite see it, to be honest. Slightly less. Still can't see it. I believe this was the way to do this. Round, round. UGents normally respond to round. Okay. My last attempt. Okay, that definitely doesn't work. Oh yeah, that does work. Sorry. So there you go, some comparison of the screen resolution and the audio resolution. So that's another type of resolution loss. Let's hear it. Let's look at the spectrum of that. A bit like this. Again, we get tons of junk. Let's look at the error signal there. So from this we subtract the S and then plot that. Sorry, yeah, plot that. That was not a subtraction. Plot that. Okay, so here's the error signal. You see it's much smaller. You can play with this. It's just a demo of things. By the way, these types of distortion are used for audio signals, recorded signals, as a strategy to essentially create non-harmonic overtones. We'll have a special class on distortion anyway, and talk about what it does. Essentially creates overtones. Cool. Shall we do both at the same time? Let's do both at the same time. So now we're rounding off the latched signal, and it looks like that, and sounds a bit like this. Not horribly exciting, obviously even louder overtones. Okay, that's that. Next one up, verify the aliasing of a square wave LF pulse. So this is a geometrically perfect square wave at 10 kilohertz. So let's again start by just making sure we get a square wave as we expect. So LF pulse AR 10 kilohertz. Let's plot that and type it correctly as well. Here it is. Looks like a square wave. So what you get is you don't see necessarily the lines to be vertical because we are actually quite high up in the frequency range. if I take a slower, let's take 100 Hertz, then they should be decently vertical, the lines. Obviously, there is no such thing as a vertical line in digital audio because there has to be a transition from one sample value to the other value. And there you go. Okay, so we're looking at a 10,000 Hertz, and then we're looking at aliasing frequencies. So what do we expect? We expect the mirroring on the Nyquist, although what I have here is a 96 kilohertz sampling rate. So that's not very helpful. I kind of wrote this exercise for a lower sampling rate, but never mind, let's just go with, so the 96 kilohertz sampling rate has a Nyquist frequency of 48. So we expect everything to mirror on 48. So let's try 20,000 Hertz. At least we won't hear it. At least the 20,000 Hertz we don't hear. Okay, so what do we get here? Well, we get the 20,000 Hertz signal there. So this is my original square wave. And then we get the aliased frequencies. So I see something here, and something here. So this is, well, let's try to predict what they are. And then we will try to use destructive interference to remove them, which I didn't try beforehand. Very exciting. So if I have a 20,000 Hertz, then the first overtone, because it's a square wave, is the odd harmonic, the third harmonic, which is at 60,000 Hertz. So essentially what I expect is that to be mirrored on the 48,000 Hertz. Okay, so the difference between 60,000 and 48,000 will be 12,000. Okay, and then because it's mirroring, 12,000 less than, it's 36,000. Okay, so let's see if that looks a bit like 36. I mean, the resolution isn't great there, but easily that's 36. Okay, so we will remember that one. One is 36,000, and then the fifth harmonic should be 5 times 20,000. Okay, so that's 100,000. So, and then minus 48,000 is 52,000. Okay, so that's way above. So another interesting thing happens there is that goes below. So actually we get a kind of DC offset, which you've seen there, but actually it mirrors back again from the zero, because negative frequencies are just as well frequencies. So it gets a bit more complex. So shall we go there? Let's just try to remove the 36,000 Hertz. Okay, so typically in a square wave, the sine waves are in phase. So actually I expect it's sufficient to just create a sine wave at that frequency and subtract that from the aliased square wave. Okay, fingers crossed. Well, no, it's still there. Okay, so what we could do is we could play with the phase of this sine wave such that we see whether there would be another phase at which they would destructively interfere. I mean, before that I can also try to add, would that make a difference? Doesn't seem to make a difference. Okay, so let's try the phase moving trick. So the phase here is 0. I believe it is normalized, the phase 0 to 1. Let's see what the help file says. Does it say somewhere something about the phase? Audio rate modulation. It doesn't say anything about the phase. Well, I'll just modulate it. So I'll take a slow sine wave there. so we see it happen. Let's take 2 seconds. And well, let's just leave it in -1 + 1. I mean, I could multiply it with pi. Let's do that. So 0 phase and a pi multiplier if the phase is indeed not normalized 0 to 1. But for some reason I seem to remember that it is. Oh, there was some phase in radians. Alright, so it's not normalized. So phase should be within the range ±8 pi. Okay, so it's not normalized. It means that the full phase cycle is 2 pi in radians. So this looks good. This will take us to +pi and -pi. Cool, let's see that happen. And there it is. So I'm kind of getting it to disappear. Almost. So I kind of verified that that is one of the frequencies. Okay. Cool. Let's leave it at that demonstration. I mean, obviously if I pick different values, I can make sure that the 5th harmonic is somewhere feasible. But what you've seen here, as I said, the mirror is both sides, so both at the Nyquist frequency and both at 0 Hertz. So you will get things kind of coming back in and out. Cool. So that's the demo. Concept proved. Let's get on with it. Number 3 says make a harmonic and an inharmonic sound out of 5 sine waves. See if changing the phase makes an audible difference. Okay, so we're gonna be adding 5 sine waves, and I will obviously you could do this plus another one plus another one, but I will show you a trick already. What you can do, I think we'll probably have this discussed at some point. In SuperCollider, what we have is an automatic expansion of arrays. So if I put multiple frequencies into an array, then I will get that amount of oscillators in an array. Okay, so any argument that is not a single value or a single eugen, but is an array of values or eugens, will expand the host eugen and create that amount of hosts and stick them all into an array. Okay, so having said that, once you have an array of 5 sine oscillators, if you play that back, what you actually get is each one playing in a different channel. So if you have 8 outputs on your sound card, first 5 will play these sine waves respectively. Now this video is mono, only the first channel. So what you actually need to do is sum these things. We have a sum command, and then the other thing that I will do is I will lower the amplitude because there will be some constructive interference there. We will go beyond 1 and thereby clip the signal and so on. Okay, so this thing is my harmonic sound. And the thing is that to me, it sounds like multiple sources. Okay, I'm not great with harmony, I probably couldn't sing it, but one of the tricks to create a a kind of a unison, a percept of a single sound source, which is actually made up of out of many, is, especially with sine waves, is to lower the amplitude of higher harmonics. Okay, so I'm gonna do that. I have 5. Okay, so let's hear this one. Probably can be more generous with the volume now. Probably even more generous. Okay, so now it does sound like a single tone, and it does have these multiple harmonics. Let's verify that. So here it is. Okay, I kind of made them quite soft. Let's be a bit more generous here. Let's see how much we can push the volume of these. What did I do there? Let's have a 0.2. How about this one? Okay, slightly more harmonically rich. Okay, so the question here is whether I can hear a difference if I have crooked phases. So we've seen that the phases go in a circle up to pi, so 0 to 6. Let's do some random numbers. Up to 6.243, 1.2, 4.5. Make it a bit more unreal because otherwise there is a common denominator. 1, 2, 3, 4, 5. Okay, I'm happy with those. And let's hear it. Providing I have not made a typo. Great. So what the hell is going on here? Oh, how did I get there? So what I was trying to do is make this the phases. So what I've done instead is I've put that array into the adder. So it was all kind of DC offset. That's why I had the plop. So here it is. Honestly, I hear quite a lot of difference. That's the spectrum of that. And now let's try to make a decent comparison. Okay, now that we're here and doing this lovely supercolliding. A decent comparison would be an A-B comparison. So what I can do is I can call this signal A, and I will create a signal B, which is the same thing but with no phase differences. So all phases are 0. And then what I'll do is I'll try to make a fade between the two. What can I do? I can use a sine wave. Let's think, do we want silence in between? Do we want an abrupt change? Let's just do an abrupt change. It will tick, but never mind that. So we can use an LF pulse, which is our geometrically accurate square wave. And what we can do is have a frequency of changing. Let's take 1 second. So that will be my, let's call it modulation signal. And then the point is to have this in the range of 0 to 1. But actually what I can do is I can type it all in the final line saying that I'm doing A times modulation dot range 0 to 1 plus something rather similar to this, which is B times M range 1 to 0. Okay, so range method is really cool and useful because you don't really have to know the original range of the signal, the output values. You can just request it to be, and it works seamlessly. So the final thing here is the order of execution in terms of maths. So in mathematics, multiplication has precedence over addition, but in SuperCollider you actually have a sequence precedence. So first things come first. So probably the safest thing is always to be explicit about the order of execution, because brackets will make that explicit. Okay, looking good. Let's hear it. Hopefully we get it. Great. Obvious difference there. Let's see this on a frequency scope as well. So obviously the ticking is this anomaly here, but actually the spectral magnitude is the same, which is kind of expected. So there you go. We do hear a difference. We can do the same thing with an inharmonic set of frequencies. So let's try that. Let's change these slightly. Some resolution here to remove the common denominator potentially. Something similar but more inharmonic. Let's hope that does something cool. Okay, so that's the array of frequencies, and then I will reuse that array of frequencies right here, and let's hear and see that one. Okay, so actually I'm a bit worried that what we had here is clipping more so than an audible difference. Let's try this with a lower amplitude. Aha, it was clipping. Great, so we've disproved what we thought we've just proved. A bit lower even, let's keep this safe. Well, I seem to think that I can hear the difference. I do. So the question is, okay, so if we are designing an actual psychoacoustic test here, is this sufficient? Well, typically not. It's what you would have to do then is create a placebo signal, so to speak. So create the same thing with ticking, whereby both are the same, and then compare it to the one when both aren't the same, and then ask, do you hear a difference between the two sounds in both cases, and so on and so forth. So there is a difference in my ears. But I might be fooled by my expectations here. Shall we try the placebo signal? Obviously this is not a blind test anymore. Now the problem with the placebo signal here is that they are totally in phase, so it's the same signal, so the modulation doesn't do a thing. So I would have to offset the phases in a unified way. Well, now that we're here getting stuck, hell, let's do that. Let's take all of them to have a different phase, so we expect some kind of clicking at least, and then this is the C signal. I might be overdoing this. What did I do wrong? Receiver. Oh, B twice, C, sorry. Here we go again. Well, to be honest, I can lead myself to believe that I hear a difference between the two, in terms of one being higher and the other one being lower. Let's try that again. But I can also lead myself to believe that they're the same thing. Let's try the original once again. Get rid of this one. I seem to hear some difference. So yeah, tricky call. Obviously, a lot of subjects, some good statistical analysis. Maybe we could get to the bottom of this. The ancient theory says you don't hear the difference, okay? But don't believe the hype, you know, test it, figure it out. Cool, so let's observe this one again, now without clipping. I think the thing that's not helpful is that the quality of the tick changes, and therefore we get a kind of a sense that something else is about to happen. I'll leave it at that, guys. Have fun with this if you feel like it gives you a sense of fun. Cool. 4. Divide an octave into 8 equal parts and create 3 chord progressions using triangle waves. Chord progressions. Okay, so that was in the previous video. How do we do that? Well, essentially an octave is a fixed multiplier across the spectrum. So whatever frequency you have, an octave on top will be double that frequency. So if we start with 440, the next one is 880, and then the next one is 7060. So the difference between the two values that form an octave is not fixed. The multiplier between the two values is fixed. Okay, so then the question is, how would I divide the octave into 2 equal parts in the way that the multiplier is fixed? So I cannot halve the difference. What I have to do is I have to take the square root of the difference. Am I saying this right? Sorry, the square root of the, not the difference, but of the ratio. Okay, so if I do 880 by 440, that's 2. Okay, so that's the ratio between the two frequencies. And then the square root is to the power of half. And this is the square root of 2, 1.4. So the thing here is that if I multiply 440 with that square root, then I will get 622. And if I do that again, then I get the 880. Okay, so I have found a fixed multiplier that will give me half of an octave. Cool, so if I want to do that, if I want to split the octave into 8 equal parts, then what I have to do is take the 8th root. Okay, so my multiplier for that will be 1.09. Okay, so what I can do then is, let's start with 440, and the next one up will be 479. So I'm not sure if copying out of there, or shall I show you the quick thing? I'll show you the quick thing. Obviously you could do this, copy all the stuff, but actually this is what we call a geometric array, which has an amount of values. So let's do well, let's do 2 octaves. Okay, so in this case that will be 17 notes, that, and then we hope to end up at 1760, so that will be a good verification. We start at 440 and we grow it, we multiply to get the next value by this 8th root of 2. So this is my array, and indeed I end up at 1760. Okay, so the task here would be to create some harmonies here. So obviously you could pick these numbers, put them into different triangle waves, but I'll do something potentially more exciting. So what I will do is I will first of all create the triangles. I've learned yesterday that there are no band-limited triangle waves, although I might be wrong. And then you've seen that it's possible to create, put an array just here. So what I would like to do then is maybe take random values out of the array. Or actually, let's not take random values, but let's select the values. So what I can do is I can put the array there. So this is my array of frequencies, and I take this array, and then with square brackets I can index into that array. So I can ask for the first value, and then I can ask for a few more. Let's have 3 values in a chord. Okay, so that will be that. And then I'm gonna sum those and multiply. Lower the volume, don't wanna get clipping happening there. So let's hear the first, the third, and the fifth. That would be a kind of a musical thing, hopefully. Okay, so what are we missing there? Semicolon here. A function that we want to play. Great. Let's see what happens with 1, 4, 5. Better. Okay, well that's the exercise. I will cut it short. I won't go into funny ways of doing stuff with this. So the final thing is to run a wavetable full of noise at 1 kilohertz and run a sine wave which has a different frequency from the wavetable that we're running at. Okay, so let's see how do we do that. Well, the wavetables are typically stored in buffers. If you look at the help file of the buffer, I believe there should be a method. So first few bits of code here have everything to do with loading sound files. And then I believe there is one which actually allows us to get data into it. Done free self. I'm not sure where I'm going from the bottom to top. Read, that's same thing. Read, allocate, array fill. Great. So here is a way to fill a buffer with an array of numbers. Okay, so let's try that. So we want to run it at a noise wavetable at 1 kilohertz. So we're potentially gonna get into trouble there. I think there was another one. There's this array fill. This one actually fills it with noise. Send collection. And this one has a play buff as well and fills it with sine waves, interleaving, multi-dimensional arrays. Okay, well, let's get at it, see what happens. So we are having a buffer. Let's take a slightly larger one, 256. And then we allocate that buffer, great. And then we set the values starting from 0, and we take random values, and then let's take them from -1 to +1. Okay, and let's see what's going on with that buffer. That is looking good. Okay, we have a buffer filled with noise, and then we're interested in playing that buffer. And for that we have the method called playBuff. Okay, AR, number of channels 1, buff num comes from B, and then comes the rate. So I'm interested how that actually works internally. I'm not quite sure. Let's see what it says about rate. 1 is the server sample rate, 2 is 1 octave up. Okay, so what I suspect then is that if the rate is 1, it will actually play every sample from the buffer as a single sample output. So in this case, let's do that to start with. So the rate is 1, and then start position is 0. Sorry, trigger is 1, start position is 0, and loop is 1. Okay, let's see what happens there to start with. Oh, sorry, it's wrong. Play the function like that. Great. Let me make that a bit softer and let's look at the scope. So one of the things that you've heard, first of all, is that it's not a noise signal as we perceive it. It actually has a very clear pitch. Okay. So the question is, what is the pitch that it has? Well, there seems to be a fundamental here around 300, but to me this sounds like a higher pitch. But not necessarily. So the question is, what is that pitch? Can we get this to play at 1 kilohertz? So what we know is that my sample rate is 96 kilohertz, 96,000. And we know that we repeat this wavetable at 256. What I can do though is I can increase this slightly. Let's have 266 and verify that the pitch is lowered such that we know that the looping is actually dependent on the duration of the buffer. And that seems to be the case. Okay, so then what I know is that I am repeating this buffer every 360.9 samples. Okay, so that's my period duration. And then let's see what I can conclude from that. I'm a bit puzzled here. So what we get is let's look at the duration of one sample. Okay, let's do this the long way around. So the duration of one sample in seconds at the sample rate is 1.04 times 10 to the power of minus 5. Okay, so then I would typically say that if that is the duration of one sample, then the duration of the amount of samples is this. Okay, so what you have then is that actually it is the same number because I have 96 in there twice. Okay, so I showed it the long way around. So this is the duration of one sample. I think I'm getting confused. Definitely getting confused here. Let's just leave it. Instead, let's just look at what happens if I put in a sine wave. So if in this 266 samples I would get a sine wave. So let's do that. So if I take the index of this iteration, this will be a number I that goes from 0 to 255. By the way, there is other ways of putting in a sine wave from the help file, so you can look into that, because obviously I'm trying to make it such that these exercises can be completed with the very few basic things that you've seen if you followed the previous bits. But let's just wrap it up and say that we get an index in there which will go from 0 to 266. Okay, so a full cycle of a sine wave is 6.28. So in here I would probably get something like 50 cycles, which is quite a lot. So what I'll do is I'll divide by 40. So let's get more than a single cycle into the array. And then I'll take the sine value of this. Cool, so here we go. Let's check that buffer didn't quite work. I by 40 sine, oh sorry, not 1 by 40, I by 40. Try again. Here it is. So indeed I got a bit more than a single cycle of that sine wave. I can try to get even more. Let's try this. Oops. this one, this one. Okay, what I can also do is I can try to zero them out after this. But let's first listen to this one, and then I'll talk about the zeroing out and a lovely Vosim oscillator as well. So let's just listen to this one. So what we're trying to verify here is that the pitch of the noise in the buffer is the same as the pitch of this sine wave, and actually also that this has the same pitch as potentially this one. So the message is that if you're repeating something in a wavetable, what you hear as the pitch is the duration of the wavetable and not the contents. So you see I've put in different frequency sine waves here, and they would still sound like at that pitch. Okay, so finally let's look a bit at creating a Vosim oscillator. Could be cool, which is a square of a sine wave in a similar fashion. So what you see, it starts from 0 and goes up to 1, and it actually gives you double the frequency of the original sine wave. And the nice thing there is that you don't get a discontinuity. So if you start the sine wave at 0, but it's an actual sine wave, it starts sharp. And this one, if you zoom in, you see it actually starts gradually from 0. So that's the advantage of such a squared sine wave. And then what we could do, typically what happens in a Vosim oscillator, is that you run them at a certain rate, which is independent of the frequency of the sine wave inside the wavetable. And then what you also do is you typically select the amount of cycles in there. So you would either cut it here or cut it here in this case. So let's just cut it at one point. How do I do this? Well, let's say that I is larger than pi dot if. Okay, so if actually if it's larger, it's fine anyway. If it's larger, we yield a 0, and otherwise we do this calculation. Okay, did I make a problem there? Yep, this hasn't been a single expression. Here we go. So now I get this. Oh, well, that didn't quite work. Obviously, I would have to do the by 30 here. So let's say that first off, I is I by 30. Then I test for I, and then I can do that. Okay, second try. Oops, still not great. Is that, am I looking at the right buffer? Let's just close all the rest. I say I type 1. That's not very helpful. Here we go, and that's that. So you get a larger buffer with a little sine wave in there, and it sounds a bit like this. So you get the harmonics, but you get a much mellower sound. What you also get is DC offset, because it's not zero-centered, this waveform. So yeah, I mean, I don't want to go too far into this. There it is. Okay, so lastly, I am a bit worried about leaving this calculation behind. I kind of tend to allow myself to forget the equations and want to challenge myself each time. So let's cheat, but let's do that task. So if this is my waveform, I can actually read the frequency here, and it does look like 266. So I was probably confused rather than anything else. Although it's suspicious. I know it can't be 266. Let's do because obviously the sample rate is 96 kilohertz, and that's significant. The thing is that it's very close to 100,000. So let me think about this problem. So I definitely, let's start again with this issue. So why did I get confused? So definitely the duration of a single sample is that. Okay. Because there is this many in a second. And then if I multiply that by 266, I get the duration of the cycle. And if I do 1 over that, I get the frequency. So that's supposed to be the frequency. Now, if I increase the amount of samples in the buffer, let's say 366, I'm supposed to get a lower frequency. Okay, so with 366 I get 262 Hertz. So to come back to the original task then, 1 kilohertz, how do I get to 1 kilohertz? Well, I would have to inverse all this. I could play with it as well. Whatever, 130, almost 120, not quite 100, not quite 96, probably. Yeah. So that would then be the actual solution at 96 kilohertz. So now I'm playing these noise at 1 kilohertz and 1 cycle of a squared sine wave at 1 kilohertz, and the pitch is the same thing. Okay, that's the end of it then. Thanks for sticking through. Cheers and goodbye.